Good evening. Well, welcome to this edition of Presidential Lecture Series. I see students and faculty colleagues streaming in, but we're going to get started here. And tonight we are very excited to have a very special treat of intellectual dialogue with an amazing intellect of our times. So Frank Wilczek, professor from MIT Physics Department, received about 20 years ago the Nobel Prize in Physics for one of his many monumental contributions to our understanding of our world, 1973 discovery with David Gross's advisor at that time of the asymptotic freedom in strong interactions among quarks in the atomic nuclei. And since then, Professor Wilczek has consistently made amazing contributions, one after another, truly a towering figure in elementary particle physics. Clearly, the original results that led to the Nobel was a cornerstone in QCD. And over the past 20 years, he's also written several books that I have been reading up as part of my homework here over the past several weeks, with an exposition of the beauty of the universe we live in and are part of. So with great pleasure and excitement, bringing on stage, and please join me to welcome a warm Boilermaker, welcome Frank Wilczek. Thank you. Thank you so much. Please. I'll sit here. You pick, whichever. They're largely symmetrical, so.
Thank you.
Well, thank you, first of all, Frank, if I may, to welcome you to Purdue. I know you've been in conversation with our physics department colleagues and so on throughout the day. I'm going to start this fireside chat by asking you several questions about specific and outstanding contributions you made, starting with 1973. So you were a young PhD student at Princeton at that time, working with your dissertation advisor, and what happened that led to the discovery of asymptotic freedom?
Well, I was looking for a thesis project, and I had just moved over from mathematics into physics, so I picked a problem that would not require a lot of knowledge of physics, but could use the mathematical tools and energy that I had. And there was at that time, the reason I moved into physics actually was at that time there was a great ferment in fundamental physics. This was the time when what's now called the Standard Model was under construction. And we had a new plausible theory of how the weak and electromagnetic interactions work, two of the four basic forces of nature. But the strong interactions were still quite mysterious. I wanted to investigate how these new theories of the weak interactions would behave at very short distances and high energies, whether they could be more consistent than the old theories, which had a problem called the Landau ghost. Anyway, I computed and found that they did have better behavior. And then David and I realized that that kind of behavior at high energies was just what the doctor ordered to describe some otherwise mysterious observations about the strong interaction. And the phenomena we discovered, namely that the interaction kind of turns off when you study it at high energies or short distances, was so unusual, so difficult to make consistent with basic principles of relativity and quantum mechanics, that it gave us basically a unique theory for how the strong interaction should work. So it was like a revelation from heaven that this is the one and only way, the one and only set of equations that could possibly be describing the strong interaction if we take quantum field theory and the certain class of experiments at face value. And that was the beginning of a long and very successful story of figuring out exactly what the strong interactions are. So we have equations at the same level of the Maxwell equations for electromagnetism or Einstein's equations for gravity that describe, in some ways more perfect, that describe the strong interaction.
Yes.
And they work.
Yeah, indeed.
Right.
And I know this room is primarily filled with already domain experts, my teachers. But in case you are wondering, this is describing the fact that under strong interactions, as the quarks get closer to each other, asymptotically, they actually do not interact, and they therefore are asymptotically free.
Yeah, even though when you take them further apart, the interaction becomes very, very strong. It's called the strong interaction because it is a strong interaction, and in fact it's so strong that the quarks have never been observed in isolation. You can't pull them out. But they're inside atomic nuclei as the basic constituents.
Oh, wonderful. Well, then later on, you postulated axions.
Yes.
People have been trying to detect it.
Yes.
What's your prediction on when it will be detected?
Well,
They almost did it.
it's hard to predict. It's very hard to predict. The sensitivity required to detect axions, if they are, as now many people, including me, think they are, the dark matter of the universe. You can pin down the properties of these particles well enough to know what it takes to actually detect them or rule out the hypothesis that they're the dark matter. And the good news is that the technology is getting there. I've been myself very actively involved in trying to improve the kind of antennas that we use to convert axions into signals that are detectable by standard electronics. So there'll be very exciting results, I think, in the next 10 years. I hope sooner, but I think at that time scale, we'll have a much better idea of whether the axions really are the dark matter.
Yes. Oh, well, maybe in 10 years' time or less, we'll invite you back here at Purdue. Anyons. So now, by the way, a little interesting story that the fractional quantum Hall effect, the recipients of Nobel, including Dan Cui, who was my office neighbor at Princeton, because he was actually electrical engineering department,
Yes.
not physics department. And he and I actually go to the same gym now and then, and I'm not sure if all the folks in the gym, he's ordered by the doctor to lift certain weights for his health condition recovery. I'm not sure if folks lifting weights there are aware of who this person is. Dan Cui was. And the other co-recipient on that prize was my instructor when I took quantum mechanics as an undergrad student. And some of you heard me tell you this true story. So while I was taking his class, Laughlin's class, he said, well, I just got a Nobel Prize, so we're all very excited. Oh, gee, the professor teaching me basic quantum mechanics just got a Nobel Prize. And then he said, I won't have time to really write your final exams. Teaching's not that important. And I have to focus on writing my Nobel Prize acceptance speech in Stockholm. So what do we do with your grades? She said, everybody gets an A. So ever since then, I lost the motivation to study. I wasn't aware of what the heck was going on anyway, so I was about to. Last week, I'm going to really study quantum mechanics. And now, I had no reason to do that, so To date, I don't understand quantum mechanics, and I tremble at the very sight of inner products and etc. So I blame that on Nobel Prize giving to Laughlin that year. But anion, that's one of the theoretical constructs that you provided, and I understand that topological quantum computing, which is wonderful excellence here at Purdue's quantum efforts here.
Yes.
And about 4 years ago, there was a very important paper published in particular. So what is your assessment on anion and on topological quantum computing versus a couple of other variants?
Okay, so I'll just take a moment to remind people what anions are. For a long time in the life of quantum theory, basically since it became modern quantum theory about 100 years ago, we've had the concept that particles have wave nature and n-particle nature. So there's something called a wavicle that unifies all kinds of quantum matter when you have single particles. But when you have more than one particle, there's more to the story. There's a division of the world into bosons and fermions that have very different properties, photons or bosons, electrons or fermions, and that kind of reinstates the duality of matter. And that's the way things stood for a long time. And it was just kind of postulated that there was this division of the world into bosons and fermions. But then in the late 1970s and early 1980s, we got curious about the idea that, we got back to examining some of the fundamental principles of quantum theory, and just making that assertion didn't seem satisfactory anymore, not very satisfying. And more than that, when we looked at some examples in abstract models that were consistent with quantum mechanics, we found that there were other possibilities. These other possibilities are called anions. They exist only for particles that that live in two space dimensions and one time. That's interesting, though, because lots of materials that we work with, like computer chips or graphene layers, are two-dimensional. So it's possible that if you have particles whose very existence is tied to the material that they live in, so-called emergent particles or quasi-particles that are in two dimensions, that they wouldn't be bosons or fermions, and that they would have different behavior, which I won't attempt to describe technically, but basically the behavior is that these particles have a kind of memory. They remember where they're, or what do I mean? They don't, of course, have brains, but their wave function remembers not only where they are, but where they've been. And this gets beyond bosons and fermions. And that kind of quantum memory could be something that's useful to store information, and also by moving the particles around, you can manipulate that information in the wave function. So that was the theoretical idea, and it was realized not long after the introduction of this theoretical concept that in the state of matter called the fractional quantum Hall effect, the particles that live there, the quasi-particles in that regime, should behave as anions, so something very new under the sun, particles with memory. And these, now, the states of matter involved are kind of exotic. They involve two-dimensional materials that have to be very pure in a high magnetic field at very low temperatures, and the requisite measurements are very difficult. Nevertheless, I thought that it would just be a matter of weeks until this could be checked. But after the prediction was made in 1984, weeks passed and months passed and years passed, and nobody was able to do it despite a lot of efforts until in 2020, a group led by Michael Manfa here did manage to control all the sources of noise and complication that obscured the basic effect and show that these anyons really do exist in the fractional quantum Hall effect. And the techniques that they introduced, and also just the demonstration that it can be done, has been very inspiring, has galvanized the physics community, and now many people are investigating other instances of anyons and other kinds of materials. A big motivation for this is not only just curiosity is a whole new kingdom of particles. It's as if biology knew about plants and animals and suddenly discovered something else. But also because they have memory, they could be very useful in quantum information processing. And because of some of the special properties of this memory, it's so-called distributed memory. It's sort of like a hologram. You can mess up part of it and still recover the image. It could have advantages for actually building quantum computers. And so that's what you were alluding to. This is topological quantum computing. But as I mentioned before, the states of matter that support anyons are mostly pretty exotic. People have experimented now with artificial materials that also can do the job. Those may be more tractable. I mean, after all, transistors are pretty exotic too when you get down to it. So I think there's a good chance that this will break through. It's not going to be easy. It's not going to be. Now I've learned my lesson. It's not going to be a few weeks, but it may be in a few years, maybe in a few decades. I think the basic concepts are sound, and the technology has profound advantages over other ones. But other ways of getting to quantum information processing, I think in the short run have advantages, but in the long run, I think the topological quantum computing will be the most. Is the most profound and deserves to be the winner. And another thing I should say is that even if anyons themselves aren't the vehicle of carrying quantum information in the short run, the ideas that went into constructing distributed memory and that arose in anyon physics are basically the same ideas that are used in the whole field of correcting errors in quantum computers, which is a very important thing because they're delicate and they do make errors. Right.
Yes. Well, I'm not biased, but I like that prediction you just made there. Oh, well, if I may now turn to, I think the first of the 3 or 4 books you published over the past 2 decades, ask you several questions inspired by your writing here. So this book is called The Lightness of Being. And by the way, you can purchase any of these from your favorite bookstores or Amazon. But now, first of all, the lightness of being here is already a wonderful play on unbearable, and then a further double pun on the lightness, as opposed to other dualities.
The basic concept is that we're built out of building blocks that have 0 mass. Mm-hmm. Our mass is emergent.
Yes.
It's basically E equals mc squared run backwards to say that m equals E divided by c squared. Yeah. our energy is basically the energy of the quarks and gluons that are moving around really fast but confined.
Mass is from energy.
The mass is from energy, yes.
Yeah. Well, you also highlighted here the notion is beauty, truth. And again, truth, beauty, truth, that's all you know and all you need to know. So at least some poets already declared it so. Now you went into some discussion of that here, starting with what the Pythagoras, or the whole school of Pythagoreans, were doing back then, and the correlation between what human beings' ears and brains would interpret as harmonious beauty in sound, somehow had some kind of relationship with mathematical ratios.
Yes.
So do you think that's because there is some intrinsic connection there in nature, or is how human beings happen to appreciate and perceive beauty?
Well, I think there's evolutionary value in getting in tune with the world and being able to understand nature in her own terms. And we do that. And we're also learning creatures. So we we're designed to enjoy ideas that are successful, that kind of explain how patterns make sense and how the world works. And so sort of an operational definition of beauty is what you like to come back to. And the fact that we like to learn things that work.
Yes, in the eyes of beholders.
Yes.
Well, actually,
makes it less mysterious why the
Yes.
things we find beautiful are the things that actually work in the world.
Maybe indeed. My wife does not believe that I have anything resembling beauty, but since she has to look at my face, she may have, psychologically hinted herself, let's pretend this is close to beauty. So you also mentioned an interesting thing, falsifiability. As Karl Popper would claim that that is a necessary, if not sufficient, condition for what would constitute a science. It can be proven wrong. Doesn't mean that if it were proven wrong, it is no longer scientifically valid, but the ability to be proven wrong. But you went a step further here, and you quoted, was it Boris or someone, that, the opposite of truth is falsehood, but opposite of profound truth is another profound truth.
Yes.
So what do you mean by, what does he mean by that, you think?
Well, Bohr was very fond of a concept called complementarity, which I also am very fond of, which is the idea that to do justice to reality, or do justice to any complex system, really, you may have to adopt different points of view that are very difficult to translate into one another, but nevertheless are valid in their own terms and answer different questions about the thing you're trying to address. So a good example is when you try to understand a human being. If you're trying to predict the behavior of a human being, you make models of mind and how that person might be thinking and what's motivating them and so forth, on the one hand. But on the other hand, if you want to know how they'll be blown away by a strong wind, or how they'll react to being exposed to a pollutant or a poison or a treatment, then you don't use that model. You use a model more based on physics and chemistry, and each of them is valid for answering different kinds of questions. But if you try to make mechanical explanations of how people are going to behave and what their motivations are, or if you try to use psychological terms to predict how someone's going to react to being blown by a windstorm, or jump on a trampoline, recoil on a trampoline, you're not going to get very far. So it may take different kinds of concepts that may even seem not only contradictory, but even untranslatable one into the other to do justice to reality. And so there can be profound statements in one language that you can't make sense of in another language, but both
Yes.
profound truths.
There's quite a bit of a duality or symmetry. We want to come back to that in a minute. But one thing that a lot of people have been debating is most people agree that physics is about discovery of nature. Mathematics, however, there's a debate. Is it discovered or is it invented?
Yes.
Say the ratio that the Pythagorean school was so proud to discover about musical pitches. Well, the musical pitches, high and low, discovering that perhaps from nature, but certain notion of scale, mathematically, one could argue, are you discovering that or are you inventing that? What do you think?
Well, some things in mathematics, I think, would occur to any intelligent species that was exploring the domain. So, for instance, in the theory of numbers, there are famous theorems about how many, there are an infinite number of primes, which is very beautiful, and there's a unique way of factorizing numbers into primes, which is very beautiful. And then if you extend the concept of numbers, it fails in a certain way, then you can fix it. I think these are inevitable things that people discover. They don't have to invent them. I don't think we really invent whole numbers. Other idealizations, you can argue, are invented, or are less inevitable, and mathematics has fads, just like other things. People, well, I don't want to offend people by mentioning particular things, but an example that I think will not offend anyone is that in the 19th century, many of the leading mathematicians in the world spent most of their attention developing the theory of elliptic functions, and that was a very big deal. And it's a beautiful subject, an absolutely beautiful subject, but then it got elaborated and kind of fell out of fashion until people, but then in the late 20th century, it came back into fashion because if you change the domain from complex numbers into more abstract quantities, they can be useful in the theory of ordinary numbers in very indirect ways. But I think it's closer to the truth to say that mathematics is discovered than that it's invented. But on the other hand, we'll soon have a test case because the artificial intelligences are getting to the point where they are winning mathematical competitions and can prove things. And I think it's just a matter of time and probably not very long before they start they'll have some kind of, we'll have something we can recognize as curiosity, and then they'll start discovering theorems of their own. And the question is whether they will discover theorems that people already know or develop interests that seem very strange to human beings. A lot of mathematics has to do with the limitations of the human brain. We develop theorems that help us capture important properties of simple situations, but there are some situations that can't be understood very simply. And so you just have to enumerate a lot of cases. And so that mathematicians tend not to like that. They like things that are clean and simple to understand once you boil it down. But for instance, the four-color theorem, the only known proofs are very complicated, but they wouldn't necessarily appear complicated to an artificial intelligence. They would have memory that they could easily access it. And you could imagine proofs that human beings can't understand at all that would seem very attractive to an artificial intelligence, and vice versa.
I want to come back to the theme of AI and the theme of simplicity, but since you mentioned the four-color theorem, and generally speaking, how extensive computing power may change the way that science is carried out.
Yes.
In addition to proving things in a way that human beings wouldn't find very appealing.
Yes.
But as you said, the machines may find it, wow, that's quite natural to me.
Yeah.
But what do you think about the access to a huge amount of computing power changing the way that science is carried out? Does that excite you? Does that worry you? Is this still science if it's mostly done by computing power?
Well, it's both. I mean, both excites me and worries me a little bit. I'd say I'm more excited than worried, but and it's happened. It's not a new phenomenon in its sense. The discoveries in high energy physics, like the Higgs particle, rely on analysis of huge data sets that unassisted human beings could never do. In fact, they make heavy use of artificial neural nets to do pattern recognition. You know, when you see a complicated event at the LHC, the tracks and the information they encode don't come with labels saying I'm a K meson, I'm a pi meson, I'm a proton. You have to interpret these pictures, and much less do they come with labels saying I'm the product of the decay of a Higgs boson. You need to analyze enormous amounts of data and have inform the neural networks what they're supposed to be looking for, and in order to do it. And you know, every day in my work, I use computers to do numerical simulations. I love, use mathematics. I love to do it. In recent months, I've taken to chatting with ChatGPT very regularly to learn about things and do searches, and so these are new tools of enormous power that are really fun to use. Now, it'll be less fun probably when the answers get too good, so that they sort of solve the problem for you completely. That will take some of the joy, I think, out of the discovery process, maybe. But I don't think we're there yet. A parallel development has happened, actually, in the world of chess, which I know pretty well as a fan. The best players in the world are no longer humans. The computers just are better, objectively, much better than even the very best human chess players. But people still enjoy playing. They play, so they have tournaments. There's a world champion, and it's still competitive as a sport. So.
And we don't run faster than cars.
Exactly.
We still run against each
That's
other.
right.
We actually invited, or I should say my predecessor, Rich Daniels, invited to the same series, Kasparov. And he asked him, do you think it's fair, the fact that, your opponent got plugged into an outlet and it's burning per second, factor of 10 to the 4, 10 to the 5th power, more energy than you do per second. And I think Kasparov's response was, wow, it doesn't matter. I don't care, I'm over it. I want to move on to this book, the recent book called The Fundamentals, 10 Keys to Reality. And at the end of your preamble there, you cited William Blake's poem, "To see a world in a grain of sand and a heaven in a wildflower. Hold infinity in the palm of your hand and eternity in an hour." There's a lot of space. There's a lot of time. There's a lot of space, quoting you. Out there's a lot of space within an atom. Can you please elaborate a bit more with this audience on that?
Well, human beings are kind of equally poised between the size of the size of the visible universe and the size of atomic nuclei, it turns out. So just in that crude way, we see that there's a lot going on inside and a lot going on outside. The remarkable and beautiful thing that I think for me is conjured up by Blake's poem is that we can understand it. You know, we can understand a lot of it, even though it's much bigger than us or much smaller than us, and we don't have to feel diminished by the fact that the universe is much bigger, because we can internalize what it's all about. It's there for our entertainment in some sense, and we can revel in the fact that we are built up out of so many components and yet sort of cohere and have properties that aren't obvious or even really defined in terms of the individual components. The atoms don't really think, but the kind of structured complexity that is necessary to support mind is just right for us. It's just, we're just big enough to have it, and it's fantastic to think. And I still sometimes have to feel that I'm waking up from a dream when I realize that the equations that we write down for the Standard Model, this very compact set of equations that refers to extremely abstract entities that obey very definite but strange rules, that doesn't look at all like our world, is our world.
Yes.
And how does that happen? And a lot of the steps are pretty well understood, but the ultimate question of how mind emerges from matter, I think, is still not understood at a very profound level. And so for students, that's something for the future. And it's a very exciting time, because we know what the relevant laws are, and we also have kind of in the emergence of new kinds of minds, artificial intelligence, sort of living proof, or maybe I should say non-living proof, that mind can emerge from matter. And there's, in a sense, there's no mystery to it, but in another sense, it's very mysterious.
Yes. Well, first of all, it's already interesting observation, the way you put it, that on the log scale, between the biggest and the smallest living things, sort of in the middle there. Now, so coming back to AI and coming back to this notion that perhaps human-made matter could also lead to the existence of mind. And 10 years ago or so, you co-authored a letter with a bit of a warning signal on how this mind emerging out of human-made matter would mean to humanity. So 10 years later, including the recent Nobel Prize going to two pioneers in AI, what if you were to write another letter today, what would you say?
I think, be more nuanced than I was then, because it's more, the general awareness is much higher level, so it could be maybe less alarmist and more reassuring. Because I think people have gotten over worried. So let me make several remarks. First of all, there's nothing new about artificial intelligence and emergent minds. Any corporation or any university has a kind of collective intelligence that's greater than the individual that make it up, and they act as a collective, and they can do things that no individual could do, so that's a kind of artificial intelligence. And we're building up an ecology of mind where we're going to gain experience, and I think it's going to happen sufficiently slowly that a body of experience and a body of law will emerge that will regulate the interactions and lead to a world with vastly increased levels of wealth. And I enjoy, at a personal level, I enjoy chatting to ChatGPT and collaborating and so forth. And I think those kind of interactions will become more human, if you like, but different. The thing that does worry me, however, really does worry me, is also, in a sense, not new, but has become much more worrisome, I think, is the use of artificial intelligence in, broadly speaking, military contexts. So if you think about the old idea of a doomsday machine, such as appeared in the Dr. Strangelove movie, what is a doomsday machine? A doomsday machine is a machine that acts on signals without human intervention and does very powerful things. And that is an artificial intelligence, you like, that may be not very intelligent, but now with the development of more powerful artificial intelligence that can detect many, many possible different kinds of threats and has very sophisticated ways of acting on those threats. If you think about a human analogy to that, it's like someone that's paranoid and also very aggressive, and that's a very dangerous combination. So I think the military uses really worry me, and I think also they're more problematic to manage because they require international collaboration, which is hard to come by these days.
Well, one of the defining features of mind, I guess, is the ability to suffer. And if these minds emerging out of human-made machines one day suffer as much as human souls,
yes.
They might decide not to be mind anymore. But human beings, I don't know, Frank, what you think, but human beings tend to be generally borderline boring. So the question is, will these machines make human beings even more boring or more interesting? I'm going to turn on to the next page here. This is another book published in between those two called A Beautiful Question by Frank. And here you, of course, would go into the particles, and you will go into some unification of QED and QCD and the weak and general theory of relativity here. And my physics friends indeed have this very strong enthusiasm of unification. You say, all right, there's the standard model, but how do we give the shortest description length?
Yes.
What's your view on the potential of a grand unification now?
Well, I see some concrete steps that we can take towards it that I'm very optimistic about. The standard model is very, very successful, terribly successful. So there are only indirect experimental clues about how to do better if you really want to do better. Physics for a long time has had the program of reductionism in two senses. First of all, in a concrete sense, trying to understand smaller and smaller things, and then building up from the accurate description of how small things work, how big things work. But more generally, as you alluded to, trying to make as compact a description of nature as possible. So getting the laws to be simpler in a very specific way that I think you can actually make fairly precise. You want to try to make the laws such that they can be, that you can teach them to a computer without loss of information in a short program. So then you try to make the program shorter and shorter. The bad news is that if you do that, to get consequences, you have to run the program longer and longer and do more and more elaborate calculations. But that's kind of the ideal that fundamental physics has held up and has worked very, very well in getting a more profound understanding of nature. Now, at present, it's been so successful that it's the rate of innovation in this field has really slowed down. All the experiments have just confirmed existing ideas now for decades, really. But there are a few loose ends. The theories are not as beautiful as they could be. And there are hints from the internal logic of the theory of how to make a more unified description. That more unified description mostly tells you that if you accept it, it's going to be very difficult to get new phenomena out of it, because the characteristic phenomena occur at much, much higher energies than are practically observable. But there are a few exceptions. I think axions is one. Axions are kind of a gift from high energies down to low energies, and they last because they interact very, very weakly. They can be left over from the early universe and make the dark matter. So that's one thing. There's also predictions about the eventual decay of protons that need to be tested. There's possibilities that when we study extreme events in cosmology, and gravitational waves from the early universe, new things will be revealed. So it's not going to be easy, it's not going to be fast, but I hope that we'll be able to get a few layers deeper.
Yes. Now, before I turn questions to the floor, just one more on this notion of symmetry you alluded to early on. And I forgot which physicist famously once said, or could be a mathematician, that it's Weil who said that, that symmetry is, if there's an X, symmetry if you do something to it and afterwards it looks the same.
Yes.
So why is symmetry such a powerful conceptual tool in your work and the work of others?
Well, it didn't have to be that way. And really, symmetry only became a dominant theme in physics in the 20th century, I would say. So symmetry of objects, as you say, is that the idea that you can change the object without changing it. So for instance, a circle is very symmetric. What do we mean by that? We mean that you can rotate it, so if you rotate a shape, it'll change into a different shape. Now, if you rotate a circle, every single point on the circle changes into another point, but the circle as a whole is left invariant. So we say and if you do that to an object with less symmetry, a lopsided triangle, for instance, you won't find that. So that's the mathematically precise concept of symmetry that has turned out to be very fruitful, not only in mathematics, but also in physics when you apply it not to objects, not to shapes, but to equations. So you find equations that can be transformed in different ways so that different symbols mean different things, but they have the same content. When you put them all together, the equations still have the same consequences. Why the equations of the world should work that way? It's a gift. I don't know why. But that has turned out to be the case. It goes together with this fact we mentioned earlier, that you can get a very compact description of the laws of nature, because if the laws are symmetric, then they describe many, many situations at the same time, because you can change the meaning of the symbols without changing the content of the equations. So you can describe many, many situations. I mean, for instance, just to make this concrete, in the special theory of relativity, which you learn that there's a symmetry that says that if you move past the world at a constant velocity, although lots of things change, the fundamental laws don't change. So you would still, what you're observing still obeys the fundamental laws of physics, the same laws that you would derive if you were not moving. And the symmetries of modern physics are kind of much more abstract than that and bring in quantum theory. They're very, very beautiful, but it just seems to be a gift. It didn't have to be that way. And you could imagine worlds where it's not the case. I mean, for instance, people, made famous by the Matrix movie, think that the idea that the natural world we think we're living in is we're actually living inside a computer program that manipulates information and makes us think that we're living in the world that we think we're living in. If you think about that, what would be the fundamental laws of that universe would be a computer program. And computer programs don't have symmetry. They're kind of a mess. If you think about Super Mario World, all kinds of things happen, and you can't get a compact description, and you certainly can't get it based on symmetry of how the Super Mario world works. So you can have worlds that can be very complicated, could support artificial intelligence and so forth, that are not described by simple laws. But the worlds we live in, or at least the world I think I live in, and we appear
I'll ask Microsoft.
we appear to live
we
in.
living?
We appear to live in. Are governed by equations with especially simple, wonderful, and beautiful properties that could come from a very, very short program with a lot of unfolding.
Yes. Well, the way you mentioned the special theory of relativity through symmetry is also the exposition methodology that Richard Feynman chose to use in his book, which I'm going to reserve that as the last question of the night. So, but first, we have some students with questions, please. Well, here, please.
Hello. First of all, thank you, Dr. Wilczek.
Yes.
For coming today and for talking to us and for your technical talk earlier. And thank you, Mr. President. My name is Rosie Hamid, and I'm a PhD student in the physics department. And I read a little bit about you, and I read that you actually skipped 2 grades in school, which inspired the question, how did your early education and early career impact and inspire who you are now, and in what ways, to be specific? Thank you.
Well, I was very fortunate to grow up when and where I did, I think, as far as having a career in science. I was born in New York City, and in a part of the city where there are excellent public schools, my family was my parents were first generation. My grandparents came over from Europe, so we were immigrant family, and they were very anxious, eager for me to do better than they did. And so they stressed education, and we were in a neighborhood with lots of families like that. And also, I grew up in kind of the thick of the Cold War, when people, well, two things. People first still remembered World War II, and when scientists kind of did magic, right? They produced these bombs and all the technology that helped us to win the war. So they were held in extremely high esteem, and also valued as kind of the shield that's protecting us from our enemies. So science was enormously stressed in school. There was also, as I was growing up, the Sputnik launch of the Soviet satellite that really energized, again, this kind of feeling that science was what the nation needed. So there's a big investment in science and encouragement of people who wanted to pursue scientific careers. And I definitely felt that and benefited from it in the New York City public schools. So my parents, my teachers, all of them were very encouraging, and it was also came naturally to me. It's what as long as I can remember, I was fascinated by big numbers and taking things apart and putting them together and things like that. So I'm not sure exactly what I'm supposed to say, but yeah,
Well,
it worked for me, and I resonated with it. You know, I was, I guess, naturally curious and naturally attracted to numbers and thinking about big questions, and so that'll.
well, thank you. Next question, please.
Yeah.
Hi, thanks again for the talk, President and Professor. I think my question is a little more boring, a little more technical on anions. So recently, this year even, companies like Quantinuum have demonstrated non-abelian topological order on their quantum computers. And these are models that are more complicated than the ones we can kind of work with analytically.
Yeah.
So my question to you is, how important do you think computational methods will be in studying these more complicated types of topological order that could give us possibly universal topological quantum computers? Thank you.
Well, extremely important. I think we need help in finding materials that will support this kind of computing, or strategies that will enable us to use the materials we have in new ways. Because the quantum Hall effect is a very difficult domain to work in. So it's strong magnetic field, very low temperatures, very pure materials, and they have to be massaged in the kind of clever ways that Professor Manfred is so good at. But there may be friendlier environments that remain to be discovered. So I hope that answers your question. And I think we're really in the very early days of coming to terms with anyons. I think we've sort of explored the properties of small numbers of anyons, but matter made out of anyons is an open field, and I think the algorithms that people have constructed to use anyons for quantum computing should and probably can be made much more streamlined and useful. So So when we do have usable anyons, we should have algorithms ready for them. Yeah.
Thank you. Let's take two more quick questions, please.
Hello, my name is Heather Martin. Thank you for coming to visit us. I know we're all very excited to get to talk to you. So my question was on time crystals. So once the system dynamics of time crystals are fully understood, do you think that large-scale materials such as metamaterials could be constructed that are resistant to perturbations? And what would be the consequences of such a material?
Yeah, I think time crystals, it seems to be flourishing. I feel very blessed that I was able to come up with a basic concept and a name that people have developed in ways that I didn't dream of in the early days. But I can only answer this question somewhat technically since it's a technical question. But I think the long-term use of time, I'm very optimistic that yes, they can be realized in metamaterials on a large scale. So, there may be uses I haven't thought of, but the use that I have thought of is that when you break a symmetry, and time crystals break time translation symmetry, when you break a symmetry spontaneously in a material, that material will resist a large class of perturbations that want to restore the symmetry. Otherwise, it wouldn't be stable. But it will not resist perturbations to the material as a whole that try to restore the symmetry. This is the lesson of the magnet, of the compass, I should say. A compass is made out of a magnetic material, and you can do lots of things to that material. You can bend it, or heat it up a little bit, or scratch it, and it still works as a compass, and will always point towards magnetic north. But there's another kind of operation that it's very sensitive to. That is, you can apply a magnetic field and then it'll point in a different direction. So the reason is that the magnetization, the fact that the needle becomes a magnet, breaks the rotation symmetry of the physical laws. And so it's sensitive. It's because all the spins have to choose some direction in which to point. Once they've chosen it, that's very robust and resistant to local changes. But if you change all of them in the same way, they can all stay happy. And so for time crystals, it would be very similar, but now in time. So you would have sensitivity to certain kinds of perturbations that are not constant in time, so to AC kind of signals of the right kind. So I think one of the long-term, and maybe not so long-term, applications of time crystals will be to develop sensors that are very sensitive to new kinds of signals that existing sensors maybe not so good at. I think particularly, I think they will be good. They could be sensitive to perturbations that kind of try to reset time, reset their displacement of time. So if you have a time crystal and it's running along and you have a clock that's getting out of sync, the time crystal can tell you that it's getting out of sync and feedback so you can correct it. So I think the construction of accurate clocks is something where time crystals could come in useful, and that accurate clocks is, well, it's a very mature and well-developed field, but there's a high premium on getting super accurate clocks that, especially if they can be portable, they go into GPS and so that kind of thing. So
thank you.
but also quantum computers will need clocks, and they'll need clocks that are kind of friendly to quantum mechanical operation. And I think time crystals could do that. They could synchronize the operation of different parts of a quantum computer. Yeah.
Thank you. Let's see if there's one more question. Yes, please.
Thank you, President. Thank you, Professor Wilczek, for visiting us. So I'm a senior undergraduate student at here in physics department. So recently, I see that people seems to find some features of traversable wormholes in some quantum many-body system in a holographic sense. So I was wondering, given our current understanding of nature, do you think the idea of building a humanly traversable wormhole or realizing human-scale quantum teleportation would be possible one day, or even like realizable one day? Thank you.
Okay, I'm not familiar with the precise work you're describing. I guess I'm not very optimistic about large-scale traversable wormholes. These many-body analogs of wormholes are not wormholes. They're not deformations of space-time that you can move through. They're kind of mathematical mappings of things that people would like to describe, to call space-times. So let me make a very general observation about wormholes. When people detect gravitational waves, which are distortions of space and time, they have to work very, very hard. The LIGO detector that finally succeeded at detecting gravitational waves is a gigantic thing, 4 kilometers on a side, and has very, very precise, accurate mirrors and lasers that enable you to detect tiny relative displacements of the 2 arms. And the relative displacements are a fraction of an atomic nucleus. So, and what causes those gravitational distortions? 2 gigantic black holes merging and liberating tremendous amounts of gravitational energy in the process. So the moral of that story is that bending space and time is very, very difficult. So if you want to bend space and time enough to make a wormhole, all I can say is good luck. Yes.
Purdue does not have funding for that. It's been fascinating, and I, Frank, usually abuse my power by asking the last question. So I'm holding the paper that you wrote for the Bulletin for the American Academy of Arts and Sciences back in 2002. And you were sort of answering this question that I had when I was an undergrad student, and many of you may had once upon a time, that, you know, I got the feeling when I was studying quantum mechanics, clearly I failed at that, or quantum chemistry, and I feel like I'm in a literature class or of some sort. Like, you know, things are just being made up. You know, so, you know, and then they have funny names, and, you know, one thing after another. It's like, is there an end to this, you know, novel, or how many chapters? And one way maybe look at the shortest description length here.
Yes.
I get it, you have now predictive power and so on, but, you know, it looks like it's a lot. But you said something very interesting and powerful, and that is, you know, there are these laws that you discover or create, and that do not have any non-conceptual quantities in it. You quoted at the end of your essay here, Einstein, and I quote, that is to say, nature is so constituted that it is possible logically to lay down such strongly determined laws that within these laws only rationally completely determined constants occur. Parenthesis, not constants, therefore, whose numerical value could be changed without destroying the theory.
Yes.
end of parenthesis, end quote, and your quote. So here's my question, which I'm going to phrase it in back to this very notion of the strange world we live in and truth, beauty. So this is Richard Feynman's The Character of Physical Law, which I try to revisit every now and then and be inspired by. So 1967, went from Caltech to Cornell to give 7 lectures. At the end, the last paragraph of the last lecture, Feynman says something, I suppose, relatable to what you said, what Einstein was quoted in your essay. Feynman said, what is it about nature that lets this happen? That it is possible to guess from one part what the rest is going to do. He said, this is an unscientific question, so I'm going to give an unscientific answer. I think it is because nature has a simplicity and therefore a great beauty.
Yes.
So your last words on beauty and truth.
Well, first let me respond to the Einstein quote, which is a radical program for physics, which we've come remarkably close to delivering on. It's exactly this program of, can you phrase the laws in such a way that you could teach it to a computer that just has access to logical operations, doesn't move around in the world or do experiments, that without losing any content, and then can you do that without? Einstein says he wants not only to do that, but to have that construction not contain any numbers that have to be fed in. And in the present standard model, we've come a long way towards that, but we would have to feed in about a couple of dozen numbers in order to tell the computer things like, what is the mass of the electron, what is the mass of the muon, and some other particles. But just a very small number of quantities we would have to well, I should say, actually the mass has units, so it's not a number, but mass ratios, you would have to tell it different mass ratios in order to enable it to construct the world. So that's not bad. It's much less than the periodic table, which has hundreds of entries, and also, you know, I mean, but we're not all the way there. So the fact that we've gotten there is, I think, what Feynman was alluded to, that it's been extraordinarily successful to try to get these boiled down descriptions, and they turn out to be, because they're compact, they have to contain enormous amounts of information in a form that sort of unfolds like a flower when you work out the consequences of the equations, and that's very beautiful. But it didn't have to be that way. We could have lived in Super Mario World, or and I don't know how to say it better than what Feynman said, which is that it's simple because it's beautiful, and it's beautiful because it's simple, and it's a great gift, and we didn't deserve it, and we should be happy that it works that way.
Well, thank you for giving all of us here tonight a beautiful evening. Frank Wilczek, thank you so much.
Okay. All right.